Hello, this is Coach Dorf. Today we're going to talk about implicit differentiation for calculus. I'm going to share my iPad here so you can see notes as I write them down. All right, here we go. So what is implicit differentiation? Well, what types of differentiation have we been doing so far in calculus class? Well, we've seen functions that look like y equals x cubed plus 4x squared minus 1. And we can take the derivative of that by doing the power rule. For example, I'll just show you. So we're going to use the power rule here. And we're all familiar that the derivative of that would be 3x squared plus 8x. And that would be the derivative. What are some other functions that we've seen? Well, we've also had y equals x squared e to the x. And we can solve that by using the product rule. And we also had things like y equals x over x plus 1, and we could use the quotient rule. And let's say we had y equals the square root of x squared minus 1, and in that case, we'd have to use the chain rule to take the derivative of these. In all these problems, what are we doing in essence to solve these? Well, this is kind of like hidden behind here, but actually what we're doing is when we differentiate or take the derivative, when we do that, we are taking d dx of both sides of the equation. So for example, suppose I had y equals tangent x. What I'm doing then is I'm going to do d dx of the left side. So I have d dx of y, and I'm going to do d dx of the right side. Now, when I do d dx of y, what I have is dy dx. All right. When I do the d dx of the tangent x on the right side, then I'm going to have the derivative of tangent, which is secant squared x. And then my variable here is x, so I'm doing a dx dx here. So on the right side, I've got my y, and so when I take the d dx of it, I get dy dx. Did I say that right? On my left side, I have my y, so when I take the d dx of it, I've got dy dx. On the right side, I have my variables in terms of x, and so when I take d dx of it, I'm going to have a dx dx there. Now, we don't usually write this down, okay, because you can almost think of that as 1. Dx over dx is like 1. So we usually just write dy dx equals secant squared x for the derivative of tangent x, or we write that as y prime equals secant x dx. Either of those are correct. So that's what we've been doing so far. And what do we notice about all these functions that we have here? Well, we've got, on all these cases, we have y on the left side. And on the right side, we have functions that all just have x's. So left side is just a y, and on the right side, we have just x's. But there are other functions that don't have that property. And so in order to solve those, we have to use a new approach to do this. So for example, if I had the function x squared times y minus x times y cubed equals 2, we see here that the x's and the y's are mixed together. So the function looks different than what we had before, where we had all y's on the left side, which are circled in red, and all x's on the right side, which are circled in green. So to do this, we'll use a technique called implicit differentiation. And whenever we say implicit differentiation, that means we're going to be taking derivatives where the x's and y's are mixed together. Like in this example here, if I color this in blue, the x's and y's are mixed together. All right, so let's look at a specific example, how we would do this. Suppose I have the problem here. Find the derivative, so we'll write that as dy dx. Find the derivative for x squared plus y squared equals 1. Okay, so what do we notice here? Well, we notice that my x's and y's are on the same side. So we're going to use this technique of implicit differentiation. And by the way, what is this equation of? What is x squared plus y squared equal 1? What does that look like as a graph? Well, it's a circle. It's a circle centered at the origin of radius 1. And dy dx would represent the tangent line at a point on that circle. And we'll see that a little bit later after we find the derivative. I'll show that to you. All right. So to compute or to find dy dx, what we do is we take d dx of both sides. So it's the same approach as what we've been doing before when we have just the y's on the left side and the x's on the right side. But in that case, we weren't always explicitly writing out the ddx when we were doing that. All right. But we'll do it here, and that will help you see what we're doing. So we've got our equation, x squared plus y squared equals 1. Now we're going to take d dx of the left side and d dx of the right side. And so that the d dx means we're taking the derivative with respect to the variable x. Now I can break that down into d dx of x squared on the left plus d dx of y squared on the left. And when I take the derivative d dx of 1 is a constant, so its derivative is 0. All right, now when I take the d dx of x squared, I think of that as just using the power rule. Derivative would be 2x, and I would have a dx because x is my variable. So that's why it goes on top, and I'm taking the derivative with respect to that. Now, when I do d dx of 2y, y is related to x, but I'm going to do, again, I'll just do the power rule, but I'll do it in terms with the variable y. So the derivative there would be, by the power rule, 2y. And now I'm going to have a dy dx. I have a y on the top because my variable I took the derivative with respect the 2y that I took the derivative of, I'm putting that y term on the top. But then the previous one where I had the x squared, I put the x on the top because it was x squared I was doing. All right, so I have that equals 0. And just like in the previous example, when I was doing the derivative of tangent like this, we will cancel out the dx dx. And in fact, as you do this more and more, you don't even have to write the dx dx. And I won't write it after this stage. But dx dx, you can think of it as just being equivalent to 1, so we don't really need it. All right, and we are looking for dy dx. So the next step I would do is I would solve for dy dx, because that's what we want. That's what the problem is asking for. So to solve for dy dx, I'm going to bring the 2x on the left side, I'm going to bring it over to the right side by subtracting 2x from both sides. So then I'm going to have a 2y dy dx on the left and a minus 2x on the right. Now, next, to get the dy dx by itself, I'm going to divide both sides by 2y. And so that's going to give me a dy dx equals a negative 2x over 2y. And I can cancel out the 2's here to end up with dy dx equals negative x over y. And that's my derivative. Notice when we do these implicit differentiation, the derivative is going to often will have a mixture of x and y's in it. Doesn't have to, but it often will. All right, and that matches that we started off with the original function or equation where we had x and y's mixed together as an x squared plus y squared equals 1. All right, what does this mean graphically? Well, again, this is the derivative, so it is the slope of the tangent line to the curve that we started to. And as I mentioned earlier, the x squared plus y squared equals 1 is a circle. So let's look at this on Desmos. So here, bring up Desmos. So up here on the left, I have x squared plus y squared equals 1, and I have Desmos graphing it, and it looks like a circle. It's a circle of radius 1 centered at the origin. Now, I want to take a point on this circle. So let's take this point 0, 1. That's right here at the very top of the circle. What would be the derivative? What would be the slope of the tangent line? Well, remember that if I go back to my original work that I had done, and I'll just show you that second here. Okay, we had dy dx, or the slope, equals negative x over y. Sorry about that. I'm not sure why my password keeps coming up like that. So we're going to look at this circle of radius 1. We're going to look at this point up here, and that point is 0, 1. That point up there. So what is the slope dy dx at 0, 1? Well, dy dx equals negative x over y, and when I plug those in, I have negative 0 over 1, which is 0. So the slope is 0, and you get this flat line like this. And when I go back to Desmos here, you can see that when I graph that in there, I get this straight green horizontal line. If I now take another point, let's take this point here, 1 over square root of 2, comma 1 over square root of 2. That's the x and y values. What's the tangent line going to look like? It's going to be this line here. And what's the slope of that line? It's negative 1. And if we go back to my iPad here, we'll see at the point here, so this is, we're looking at this line here, that point there is 1 over square root of 2, 1 over square root of 2. What is dy dx? Well, again, we figured out that that was negative x over y. So when I put in those points, I get negative 1 over square root of 2 over 1 over square root of 2. And if I multiply top and bottom by square root of 2 over square root of 2, then I get negative 1 over 1, which is negative 1. And that's the slope. So the slope of that red line at 1 over square root of 2, comma 1 over square root of 2 is negative 1. So this approach that we've used here in solving for the derivative when the x's and y's are mixed together gives us the same type of answer that we get when we did previous derivatives. When we did the power rule, when we did the product rule, the quotient rule, the chain rule, they all gave us the slope of the tangent line. All right, so let's do another example here. Let's look at this example where we have the function. We're going to try to find dy dx. for x squared minus y squared equals 3. So how do we do this? Well, we do the same thing. We're going to take d dx of both sides of this equation. So we have d dx of x squared minus y squared on the left and d dx of 3 on the right. And so then we have d dx of x squared minus d dx of y squared equals, and then I take d dx of 3 and I get 0 because 3 is a constant. And now on the left side, I take d dx of x squared. Again, I'm going to treat x squared, just do the power rule on it. So the derivative of that would be 2x. And I would have a dx, which we can think of as 1, and I'm just not going to write it anymore. Then I have minus d dx of y squared. So I treat y squared, I do the power rule on that. So by the power rule, I get 2y. But now y is different than the x that I have in the bottom. So when I take the derivative implicitly of y squared, I get the 2y, but I also get this dy dx. Right? And then I solve for dy dx. So to do that, I'm going to subtract 2x from both sides. So I get, on the left, I'll have minus 2y dy dx. And on the right, I now have brought over the 2x, so it's a minus 2x. And then I'm going to divide by the negative 2x on both sides. And I get dy dx equals, and before I write that, I'm going to notice I can cancel out the negatives and I can cancel out the 2's so that I end up with x over y. And that's the derivative of that. Now, what is the equation? Remember, our original function was x squared minus y squared. Oops, that's a y squared. Okay, let me go back and fix that. Okay, x squared minus y squared equals 3. That was our original function. That is, if it had a plus in there before the y squared, it would be a circle. But because it's a minus, it's a shape that's called hyperbola that looks like this. And we have a point 1 here and a point 2. This is -1, this is -2. And one point on this curve is the point 2, 1, right? You can check that. That if I take the point xy equals 2, 1, that it is on the curve x squared minus y squared equals 3, because I put in 2 for x and I put a 1 in for y, and that's going to give me, oops, that's going to give me a 4 minus 1, which equals 3, and 3 matches the 3 that's over here. Okay, so what's the derivative? So recall that we got dy dx is equal to x over y, right? That's what we got here in red. So we bring that down here. We've got that. And so what's going to be the slope? So at the point 2, 1, which we said is on the curve, dy dx is going to equal 2 over 1 or 2. And so slope of the tangent line, which I'll do in purple here, is 2, and that looks kind of like that. We can check this 2 on Desmos. Let's see, going here. Yeah, to move this down a little bit. Here, so here is the curve. I've plotted x squared minus y squared equals 3, and I get this hyperbola here. There's the point in green of 2, 1, You can see 2, 1, and the slope is 2 at that point from the dy dx that we just showed, and I can solve for the y equals mx plus b to get the tangent line, and there's the tangent line. So works again, just like we wanted to do. Okay, going back now to my iPad, let's do another example. Let's get back into black here. So, example. Okay, so we've done 2 examples so far. Let's do a little bit more complicated example. But it's going to be the same type of approach. We're going to find dy dx. We just have a different equation. 2x squared plus xy minus y squared equals 2. If you're interested, the graph of this one is like a hyperbola, but it's slightly tilted because of the x, y term in the middle and the 2 that's in front of the x squared. So it's a slightly tilted or rotated hyperbola, but basically that's the shape of it. We don't need to know that though to find dy dx. All right, so what do I do? So just like before, we take d dx of both sides. And I'm going to just go ahead and on the left side do d dx of each term. Get this, and on the right, get d dx of 2. Now, how is this problem a little bit harder than the previous problem? Well, the hard part comes in that middle term on the left side. You've got the d dx of the xy. We have to, here, the hard part is we have to use the product rule because we're multiplying 2 terms together, x times y. So that's how this one gets a little bit harder. All right, so let's look at the left side. We do d dx of 2x squared. So I do that derivative by the power rule. I'm going to bring the 2 out front, so I'm going to end up with a 4x, and I would have a dx, but I'm not going to write that. And now, what do I get for the next term? Well, doing the product rule, I've got the first term, x, times the derivative of the second, so that's d dx of y, plus the second term, which is y, times d dx of the first term. That's the product rule. All right. Then for the next term, I have I have minus d dx of y squared. I take that derivative. That's by the power rule is going to be 2y, and I'll have a dy dx. And then on the right side, we have 0. Often you'll find on many of these problems that you'll have on the homework or examples like this, you do get a 0 on one of the sides because I'll have it as a constant. Okay, now finishing the product rule here, we're going to have x. Now I do d dx of y. Well, what's the derivative of just one variable? It's going to be a 1. So this is going to be, sorry, not plus, but so I got my x here. It's going to be a dy dx. The derivative of y is going to be just 1, and then because my term has a y in it, I have to have the dy dx. Then I have plus y, and now I do the derivative of x. What's the derivative of x? Well, it's 1, and then because it's an x, I'm going to have a dx, and I don't write that down. So I just have a y. You could think, if you wanted to, that it's y times 1, and you've got that. Okay. And now, just like before, we want to solve for dy dx. So in this case, we want to put everything that has a dy dx on the left-hand side and everything that doesn't have a dy dx on the right-hand side. So I'm going to color those. 4 doesn't have any dy dx, and this y variable doesn't have any dy dx. So I'm going to bring those over to the right-hand side. And then I'm going to have an x dy dx minus 2y dy dx on the left-hand side. And on the right side, I'm going to have minus 4x minus y, because I've subtracted the 4x and I subtracted the y to get it from the left side to the right side. Okay, now to get dy dx by itself, I want to factor out the dy dx. So I'll have a parentheses, x minus 2y times dy dx equals negative 4x minus y. And now I'm going to divide everything by minus 2x. Oh, sorry, that's not right. Okay. Divide everything by x minus 2y. And so then you end up with dy dx equals negative 4x minus y over x minus 2y. And that's an answer. Now, the book, if this were a problem from on the homework, they probably would not write the answer like this. They would probably write the answer as 4x plus y over 2y minus x. That's probably how they would answer it. How did they get that from what we had before? Both answers are correct. How did they do that? Well, what they did was they probably thought in their mind, they don't like all the minus signs on the top. So they're going to multiply the top and the bottom by -1. And when you do that, you get a 4x plus y on the top, and you get a minus x plus 2y on the bottom. And then also the book probably doesn't like to have a negative x first. So they're going to, in the denominator, they're going to switch the order of the negative x and the 2y, put the 2y first. And that's why they probably have an answer like that. Okay. Which answer is the other answer, the original answer we had, this one I'm going to color here in green. Is that correct? Yes, it's correct. Do you need to know that both are correct? Yes, because if this is a multiple choice question and you got what's circled in green and the answer they give is the one in red, you need to know that you can go from the green to the red to get the correct answer in a multiple choice test. All right. Let's see. Let me do another example. Today's just going to be a bunch of examples. And I think that will help you see how to do these. As a reminder, I've got my lecture notes, and in my lecture notes, there are further examples. Most of the examples I'm doing here on my iPad are different than the examples I'm doing that are in my lecture notes. So you can see more examples of these. Also, remember, I've got the other videos of doing some homework problems that will help you too. Okay. All this is to help you succeed. That's my goal, help you to succeed. Okay. So another example. Find dy dx for 4 cosine x sine y equals 1. Okay. So this one, I look at this one, the x's and y's are mixed together on the left. And because of that, because I don't have y equals something, y on the left and all the x's on the right, then I'm going to use the implicit differentiation approach. Now, some of you may say, well, we could bring the cosine x to the other side, to the right side, right? And then you would just have a y's on the x and on the left and x's on the right. Okay. Because in that case, you would have something like, if you did that, let's say you brought the cosine to the other side. So you did that by maybe dividing by cosine. And so you'd have something like this. Well, you still don't have y by itself on the left side. Now, there are things you can do to try to get y by itself. You could bring the 4 over from the left and bring it over to the right side. And then you'd have to do the inverse sine. But we don't even know what the derivative of inverse sine is. And so that gets really complicated. So we're going to not do this approach here. And it's just easier to just do implicit differentiation. So what do? Hopefully you're seeing this pattern here. I'm going to take d dx of both sides. So I'm going to get d dx of the left side, which is 4 cosine x sine y, and ddx of the right side, which is ddx of 1. Okay, and now when I do this, what do I get on the left side? Well, 4 is a constant, so I don't have to worry about that. I am going to have to use the product rule because I have cosine and a sine in there. So I can bring the 4 out, and now I'm going to do the product rule on cosine x times sine y. So I do the first cosine x times the derivative ddx of the second. So first times the derivative of the second plus the second times the derivative of the first. And that's what I get on the left-hand side. And on the right side, I get 0 again, not something you haven't seen before, okay? All right, now I'm going to continue with this. So I have now cosine x, d dx of sine y, the derivative of sine is cosine. Make sure you don't get your x's and y's mixed up here. All right, I'm doing derivative d dx of sine y, so I should have cosine y and then a dy dx, because my variable is a y, so I'm going to do a dy dx. And then I have plus sine y. And now I do d dx of cosine x. The derivative of cosine is cosine is minus sine. And this is going to be a dx. Okay, so I'm not going to write that. I'm just going to have this. Okay. Now I could multiply the 4 that's outside the square brackets to both terms here. So I would have a 4 in front of the cosine x and a 4 in front of the sine y. But I could also just go ahead and divide by 4 here right away. And when I do that, I'm also going to bring this negative out front. I'm going to have this. And what is 0 divided by 4? It's just 0. So I just have 0 there. I'm going to cancel that out because 0 over any non-zero number is 0. And now I want to solve for dy dx. So I'm going to bring everything that's not next to dy dx, so that which means the sine y and the sine x, I'm going to bring them in blue. I'm going to bring this to the other side. And I have cosine x, cosine y, dy dx equaling, because I'm going to add sine y and sine x to get it to the other side. I have a positive sine y, sine x. And then I'm going to divide everything again by cosine x, cosine y. So I'm going to get dy dx equals sine y, sine x over cosine x, cosine y. And this is a perfectly fine answer. But again, on a multiple choice test, or if you were looking at an answer maybe in the back of the book, they might not write the answer this way. And what they could do is they could notice that I'm going to change the order of what's on top. So I have a sine x on the top and sine y, and on the bottom I have a cosine x and a cosine y. And I can break that up into 2 fractions, sine x over cosine x times sine y over cosine y. And what are those? Well, sine over cosine, as long as the x and y's are the same, are tangent. So this is going to be tangent x, tangent y. And that's probably the way the answer is written in your book, okay, or in a multiple choice example. Okay, so let's see, I've done those examples. Let's see, what next example do I want to do? Okay, let's do one more like this, just to show you again what the image looks like. So so when we take this derivative, what does it actually mean? So here's a problem written a little differently. Find the value of dy dx at the point 1, 1 for x cubed minus x times y squared plus y cubed equals 1. Okay, so I'm going to again find the derivative, but once I find the derivative, then I'm going to plug in the points x equals 1, y equals 1, and then that will give me then the value of dy dx at that point, which in other words means it's the slope of the tangent line at that point. So, so first, we want to first find dy dx. And how do I do that? By taking ddx of both sides. Again, there's a pattern here. Hopefully you're getting used to this pattern. So I'm doing ddx of x cubed on the left minus ddx of x times y squared plus ddx of y cubed. That's all on the left, and a ddx of 1 on the right. Okay, then I have ddx of x cubed. That's going to be 3x squared. Now I notice I'm going to have to do the product rule again. So when I do the product rule, this is going to be big square bracket because I had that minus in there. It's very important to have the big square bracket there. So you keep that minus sign and distribute it through everything when you get done taking the product rule. So I'm going to have x times ddx of y squared plus y squared times ddx of x, right? It's the first times the derivative of the second plus the second times the derivative of the first. And then I have ddx of y cubed, which is 3y squared with a dy dx. And on the right-hand side, I've got 0. Okay, so then we have 3x squared minus, and then I have x times derivative of y squared. It's going to be 2y dy dx plus y squared. And then I do ddx of x, which is just going to be 1, and 3x squared dy dx equaling 0. And now I'll make sure I distribute this negative sign here to both terms inside the square brackets so that I have 3x squared minus, I'm going to put 2xy dy dx, and then I'm going to have minus y squared, and I'm going to have plus 3y squared dy dx. And then what do I do next? Well, after you've done after you've taken ddx of both sides, you now solve for dy dx. So I'm going to take everything that doesn't have a dy dx, put it on the right-hand side. So that's these two terms. They're going to go over here to the right-hand side. And I'm going to be left with a negative 2xy. And at this point, I'm going to skip a step. Hopefully you can, hopefully it's not a problem for you. On the left-hand side, I'm going to keep everything that has dy dx. And so I'm going to, now forget it. I'm just going to do it. I'm going to show you all the steps. Okay. It's probably just as quick to do it this way. So when I bring the 3x squared that's circled in blue to the right-hand side, I get negative 3x squared. And when I bring the minus y squared to the right side, I'm adding y squared to both sides. So I've got plus y squared. And now I can factor out the dy dx on the left-hand side to get this. And some of you can go ahead and maybe skip a step by doing that factoring that I did on the left-hand side right away, maybe a step earlier, but it doesn't really matter. It's just, in writing it out, it's faster, but for me to explain it, I think it's about the same amount of time. And now I'm going to divide both sides by what's in the parentheses to get dy dx by itself on the left-hand side. And on the right-hand side, I have this. Okay, so there's the derivative, and that's the slope of the tangent line. And now the original problem, remember, said, I'm going to show you here, it said, find the value of dy dx at the point 1, 1. So now we're going to take at the point 1, 1, I'm going to do dy dx. I'm going to put in 1 and 1 there. Now, sometimes I see this written like this. So I have dy dx, I have this big long line after it, and then I have this 1, 1 at the bottom, and that means that you're going to be evaluating the dy dx at the point 1, 1. So x is 1, y is 1. All right, so now I just do that. I plug in 1 for x and 1 for y. And I'm getting this. And now when I simplify that, I get -3 plus 1 on top, and I get 2 plus 3 on the bottom, and that's going to be a -2/5. Oh, let's see. Something doesn't look right. Oh, yeah. So I made a mistake. Does anyone notice what the mistake I made? Well, I made a mistake here. I had this negative here, but when I divided it, I didn't put that down. Okay, so that should be a negative, that should be a negative, that should be a negative. That means that here should be a 1, and we get -2 as the answer. Okay. Yeah, sorry, I make mistakes sometimes, but we corrected and fixed it up. Now, what is this? Let's go back and look at this again to see what this looks like in Desmos. Okay, so here is this curve in Desmos. I've got this x cubed minus x y squared plus y cubed equals 1, and it's this red line in Desmos. Here's the point 1, 1 right there. And now, if I want to find the tangent line here, it's going to be this line. It's going to be this line -2x plus 3. Now let me go back. I haven't shown that, so let me go back and do that here. Okay, what is the equation of the tangent line? Now the problem didn't ask you to do this, but I want to do this just so you can see, be reminded how to do it, and that you can see that the line I showed in Desmos is the correct line. So what's the equation of a tangent line? So it's going to be y equals mx plus b, m equals the slope, and the slope is the derivative evaluated at that point 1, 1, which we figured out was -2. So there's the slope, that equals m. So I have y equals -2x plus b, and we're looking at the point x comma y equals 1, 1. So I put in 1 there, so 1 in for y equals -2 times 1 for x plus b. So I get 1 equals -2 plus b. Bring the -2 onto the other side by adding 2 to both sides, and I get b equals 3. So we get y equals -2x plus 3. That's the line of the tangent, the equation of the tangent line. And now if we go back again to Desmos, you'll see that is that green line right here. Y equals -2x plus 3. That's that tangent line. Okay. Okay, now there's one last idea I want, I believe I just need to talk about. Okay, so going back to my iPad here. All right, and this is how to find the second derivative implicitly. Okay, we found the first derivative, dy dx, that's the same as y prime. How do we find the second derivative? All right, and we'll do this that doesn't really sound like a great question, but anyway, yeah. How do you find y double prime implicitly? How do you find the second derivative implicitly? Let's look at an example. Okay, so we're going to now, instead of finding y prime, we're going to find y double prime for 9x squared plus y squared equals 9. What's the equation of this? What does this graph look like of this equation? What is the equation? Okay, let me start over here. If I had this 9x squared plus y squared equals 9, what does the graph of that look like? Well, because there's a 9 in front of the x squared and there's a 1 in front of the y squared, in other words, because the number in front of the x squared and the number in front of the y squared are not the same, this is an ellipse. Okay, it's not a circle. So it will look like something like this. So kind of like a flattened circled, okay, or this like squeezed in the side circle. All right, then you can see here the point 1, 0, x is 1, y is 0, satisfies that equation, and also the point 0, 3 satisfies the equation. So that's my shape, and that's called an ellipse. You don't need to know that. That's just for your enrichment, okay? And for some of you, that's really maybe exciting. For me, it's exciting too. But okay, if you're not exciting for you, just put it in your bag for Friday night date night things to talk about. Okay, so we want to find the second derivative for 9x squared plus y squared equals 9. Well, what we're going to first do is find the first derivative. Same thing like when we would find the second derivative for another equation. So let me just do this as recalling. Let's just suppose you had if y equals let's just say 3x to the 5th minus 2x to the 4th plus 1. The first derivative, you would just do the power rule. So you'd get 15x to the 4th minus 8x cubed. How do you do the second derivative? Well, the second derivative is the derivative of the derivative. So I'm going to just take the derivative of what I got here. And that would be, again, by the power rule, I'm going to do 15 times 4. So I'm going to get 15 times 4, x cubed minus 8 times 3, x squared. And that's going to be 60 x cubed minus 24 x squared. So to find the second derivative, you take the derivative of the first derivative. Okay, so in our problem, we've got 9x squared plus y squared equals 9. Okay, first find the first derivative, okay, which is dy dx. So I do it just like we've done before. We'll do d dx of both sides. All right, and then when I do d dx of 9x squared, that's going to be 18x with a dx, which I leave off. And then I've got a 2y dy dx, which I need to put in there. Got to have that dy dx. And on the right-hand side, I've got 0. So now I bring the 18x to the other side, and I get 2y dy dx equals negative 18x, because I subtracted 18x from both sides. Divide. Next step is to divide both sides by 2y, and I get dy dx equals negative 18x over 2y, which I can reduce by 2. And so I'm going to end up with a negative 9x over y. So there's the first derivative. Okay. Now find y double prime. Okay. I'm going to change that a little nip on my pen here. Okay. So to do this, we're going to say we're going to use the fact that the second derivative is the derivative of the derivative. Or you can think of this y double prime is d dx of the dy dx. Okay. And in some books, this will be written, you could write this d dx of dy dx is written as d with a 2 above it, y dx2. Okay, so that represents, this is the same thing as the second derivative. This means second derivative. And what's happening here, you've got 2 d's on the top and 1 y, and on the bottom you have a dx and dx, and so the 2 at the end in the denominator kind of represents that you're doing dx squared, so dx times dx. Okay, but really it's just a dx2. Okay, so anyway, if you didn't understand that, no problem. That was just something I wanted to explain to some, in case you see that again, especially if you're going to go and take further math classes where you have to do derivatives. All right, so what do? We're going to take the derivative of the first derivative. So recall the first derivative was negative 9x over y. So the second derivative is going to equal d dx of dy dx, which means I'm going to do d dx of negative 9x over y. So how do I take the derivative of negative 9x over y? Well, I have to use the quotient rule. Okay, because it's a fraction, or actually a rational expression, but it looks like a fraction. Okay, so what is that? So then we get the derivative of this, negative 9x over y, by the quotient rule would be the denominator times the derivative of the top. And when I'm doing the derivative, it's going to be d dx. So it's y times d dx of negative 9x minus the top, so minus a negative 9x times the derivative d dx of y, all over the denominator squared, which is y squared. Okay, so now we're going to just have to simplify it by continuing to take the derivative. So now I've got, in the numerator, I've got y times d dx of negative 9x. Derivative of the d dx of negative 9x is just going to be negative 9. All right, dx dx, which I'm not writing. And then I'm going to have plus. Then we have a plus here because we have 2 negatives there. And now I've got a 9x. And now I'm going to take the derivative of y, so d dx of y, that's going to be 1, and then times dy dx, and all over y squared. So cleaning that up, that looks like negative 9y plus 9x dy dx all over y squared. Okay, now here's where the first thing comes in that's really important. My answer here has a dy dx in it. We don't want that. We want to get rid of this. So what can we replace that with? Well, what is dy dx? If we go way back up here, dy dx is negative 9x over y. So this is negative 9x over y. So we're going to replace that here to get rid of the dy dx. So we have, on the top, we have negative 9y plus 9x times negative 9x over y, all over y squared. Now, we don't like that fraction in the numerator part, so we're going to simplify that. I'm going to get negative 81x squared over y. So I'm first going to multiply these two terms together to get this. Now I want to get rid of that y in the numerator. I want to get rid of that. So how do I do that? I'm going to multiply the top by y and the bottom by y. All right, so when I multiply the top by y, I have y times this, which is going to give me minus 9y squared. And then I have y times this. And when I do that, the y in the denominator and the y here cancel out. And I'm just going to get minus 81x squared. And then in the denominator, I'm going to get a y cubed. Okay. Now that looks like a final answer, but as has happened in the past, and we've seen, this is not necessarily the answer that I have in the back of the book. So what can I do to this? Well, I noticed that if I factor out a -9 from the top, I have -9 times parentheses y squared minus, plus 9x squared on the top over y cubed. And does this look familiar? In particular, does this look familiar? Well, this was the beginning, the original problem had the equation y squared plus 9x equals, what was it? I think it was 9. Let me check my notes. Yep, it was 9. So we're going to, so substitute 9 in here. Okay. So when I do that, oops, let me get black again here. I'm going to have -9, and I'm substituting in the 9 here. And in the bottom, I've got this. And you end up with an answer of that. Now, some questions I think that maybe some of you would ask. Could you have stopped? I'll do this in purple. Okay. Could you have stopped here? Or sorry, maybe not there. I mean here. Okay. This one. Could you stop there? And the answer is no. Don't stop there because you have a dy dx in there. You need to get rid of that dy